So let's get started, everyone. So thanks for coming today and so braving the cold weather. So it's supposed to warm up a bit after today. So hopefully that's good. So so I'm starting with the brain teaser. So it's been up on the screen for a few minutes. So has anyone solved this one? Yeah. You should switch. Okay. So why should you switch? So I'll repeat that for everyone. So what was proposed is that there are two possible outcomes, that there are two envelopes that have either $10 and so $20, and or that they're $20 and so $40, that these are the two, so that let's see, that these are the two possible outcomes, right? And so either you're in this state, so you're in one of these two pink states, and if you switch, then something called the expected value, which we haven't talked about in class yet, would be larger if you switched, right? If you keep your own envelope, you're going to get $20. If you switch, you might get 40, you might get 10. And if those are equally likely possible outcomes, then you would expect to get more dollars if you switched. All right. So okay, there was another hand up. Did you have, basically the same reasoning? Yeah. So this might be the right answer, but this might not be the right answer. So I didn't tell you that these two blue outcomes here are going to be so like equally likely, right? So it's not totally clear that the second one is as likely as the first one, right? So what if I said, well, there's like one bill in each envelope? Yeah. Yeah. So if there's no such thing as like a $40 bill, then the options are 10 and 20, 5 and 10, maybe 1 and 2, but you haven't seen 1 or 2. So then the options might only be 5 and 10, and so 10 and 20. And then if you switch, well, you'd have to be then you would know that this bottom state with 20 and 40 didn't actually exist. So I didn't tell you that information. But I didn't tell you that there is exactly one bill in this envelope, right? I just said, well, one envelope is twice as much money as the other envelope. So, okay, so I'll probably leave this here. We'll maybe come back to this example when after we talk about expected value. But so if you assume that these two outcomes are going to be equally likely, which might be the case, then yeah, you're better off to switch, right? But they might not be equally likely. Yeah, so this is one of the, so this may seem like, okay, this is some toy problem, but when you're dealing with probability and like statistics, as we'll see, you have to kind of make some sort of assumptions about the world, and they're not always given to you in the problem. In class, they're usually going to be given to you in your homework assignments and on the quizzes and the tests, so we can grade it, and there's exactly one answer. But in real life, that's not always the case. This might be one of those scenarios. Yeah, but if you think about this more and you think you have a kind of another explanation, so you can come tell me, maybe we can discuss it. In a future class, I'll probably bring this, as I said, I'll probably bring this back up when we talk about expected value again. Okay, let's look at the schedule here. So we are finally finishing up chapter 3 of the book. We're going to do Bayes rule today. So then we'll move on to random variables, discrete random variables on Thursday. So quiz 2, as I mentioned, was a little bit different than the other quizzes in that it was not multiple choice. There were a few I think as a whole, the class did about as well as I was expecting, so that's fine. There are a few people who had a little bit more trouble with the showing the work in the box. A couple people asked me about also being able to upload something to show your work. Again, if you get the correct answer, and I hope that the calculations are straightforward enough that you should have plenty of time, to get the right answer on these sort of questions. But if you get the right answer, then you'll get full credit on the quiz. Do people feel that it'd be helpful to be able to upload something? Say if you wrote it on a tablet or you took a picture and upload it quick, yeah? Yeah, okay, so, yep.
But I spent maybe 9 formatting my answer of my work.
Yeah, so that's okay. So in the past, if we just allow you to put the answer, everyone's like, well, I want a shot, at space to show my work, so we can get partial credit. About most people who didn't get full credit got partial credit on this one, so we're able to do that. It was good. But then I would try and get the answer you think is right first, and then go and show your thinking. That's probably the best strategy for doing this. It should be, I hope we design these so it should be pretty quick to get the answer, and then go and show your thinking is probably the right strategy. Sometimes you may work out some work to kind of derive it, but you may not. Again, the strategy of get the right answer in there and then format your work, that seems like the right approach, right? Because if you get the answer, you get full credit. Yeah. What can you... Oh, if there's another, so you could... Yeah, so I don't want you spending all day to show your work, or you got the wrong thing, then you're calculating it, and I'm hoping it should be pretty straightforward to get the right answer, and then just be able to show your work. I could do something where you can only view one question at a time, and then you have to upload your answer, and then you can show your work afterwards. But I don't feel that's the best approach, and I'll probably just allow more ways to upload, but I'll just suggest a strategy that get the answer in there and then show your work. I think that'll address 90% of the issues, I'm guessing, right? So it's mostly in case you made a mistake, then we can give you partial credit, right? So answer it first and then worry about showing your work. Yeah. And we won't always have calculations. Sometimes it'll be multiple choice or, something else like that. So okay, great. So let's do that. Also, homework 2 is now officially released. It should be in Gradescope. So if you're done, you can, you can turn it in. Like last time, I brought a few more copies because there were a couple people came up after class and I had run out of copies. So I've got some printouts for homework 2 in front. In case you don't want to print it up, come up after class and grab them. If so if you'd like to do that, that is due in a couple weeks. And I believe after the lecture today, you should have all the material for it. We will be a little bit more careful about structuring it this way. So you'll have, after we complete the material, we'll aim for a week after that to finish the homework, right? So the first homework was a little bit, we're trying to get everything on track, but we'll try and organize that from now on. So the next one will be more focusing on the discrete random variables. Also, I mentioned a couple other things in the announcement on Canvas. We will be starting just a little bit to get into R in this class. The week from Thursday, we'll be doing some stuff in R. It's not going to be too strenuous, mostly for exposure. I'll say more about it then. But if you didn't see that announcement, you might want to at least figure out how to get something running in R, and then we'll go through some pretty simple examples of just plotting, mostly plotting functionality at this point. It's mostly useful in statistics. Statistics is the part of the class where you actually deal with data. Probability is more kind of the foundational stuff, so it's less relevant to actually do some like programming. It's more for like the analysis of stuff. But some plots will be useful. And then you may have seen a flurry of announcements. There have been a number of kind of small changes to the office hours because of some scheduling conflicts and various things. So I've kept this pretty well updated on the web page. So just kind of double check. We had to move so some of the rooms for various reasons.
No.
Okay. In the past, I created. Okay. Great. So you can hear me again now? All right. I don't think you missed anything important. All right. Okay. Just talking about the office hours. We'll just leave them up on the website. Okay. Great. Yeah. So let's get into the lecture. Oh. Yeah. Yeah, so if you couldn't hear Anna, this is Annabelle, who's one of the TAs. She couldn't make her office hours today, so she'll have them after class, an hour after class on Zoom, and there might be some in-person options if you look on Canvas. All right, great. Okay, and I'm not on mute. Okay, good. All right, so let's talk about BayesRule. All right, to get started, what BayesRule is about if I have two so events A and B, I want to think about probability of A conditioned on B and the probability of B conditioned on A. And I want to know, are these equal to each other? We've seen some probability relations and some set relations where you can swap the order of things. Is this one of the cases here? So I want to, before we jump into this, I actually want to do a thing where you talk with your neighbors, and we'll do some breakout rooms. I just want you to discuss. Some of you may know the answer. In that case, try and convince your neighbor that you have the right answer, and your neighbor should be skeptical if you don't know the answer already. All right, well, so does everyone know the answer? No, okay, well, so go discuss with your neighbor, try and work it out, draw some Venn diagrams, write down some examples. Let's you can close the breakout room. So okay, everyone. So let's so do you have the answer? So who thinks that they're equal? Who thinks that they're not equal? Okay, good. So how do you figure it out? Okay, yep. So they could be equal is what you're saying, but it has to be sort of like Lewis Carroll, description to explain it. Do you have like like a mathematical way of thinking about, or like a Venn diagram way. So everything you said was correct, right? But it was a little bit hard to parse.
So, in order for A given sample given A,
Good. So this is the probability of A intersection B divided by the probability B, right? Okay. 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 So what's happening here is the numerator is the same, right? But the denominator is not the same. Right. So if the denominators are the same, the probability A and the probability B are equal, well, then it's true. But if they're not equal, then it's not true. Or it's not necessarily true. That would be a condition where it'd be true. Or they have to be true, right? Because so it's true. Yeah, we can say that this is true if the probability of A is equal to the probability of B, right? Because then the numerators have to be the same, and then the denominators are also the same. So is this your argument, or was there another point you were trying to make?
like you also say that
All right, so you're talking about a Venn diagram?
Yeah.
Okay, great. So we have a Venn diagram, and now we have A, and we have B.
so if there is same amount
Okay, so you're saying if we look at the percentage of A that is true restricted to B, compared to the percentage of A with respect to the whole sample space, then it would be true. So, all right, so if that would be if A is independent of B, right? Because that would be if A is independent of B, that might be true. But you could still, that might not, then B would be independent of A also, but the probabilities of A and B might not be the same. So I could draw a picture. So I think it's good to draw a Venn diagram, but I could have, remember I drew these strips. I could say this is A, and this condition is B. I've switched up the colors here. Okay. So now they are independent of each other. If I restrict to B, the percentage of A that falls in B is the same as the whole percentage of A. Right. So A only depends on the y coordinate, and B only depends on the x coordinate. So the percentage of A that's in B might be 10%, and the percentage of A overall is also 10%. Right. So that makes them independent, but it doesn't make this inequality, or this inequality, right? Because if I restrict, let's see, if I restrict to B, I get 10% probability of A. That's the left-hand side, right? So the left-hand side, I restrict only to B, right? And then I get 10% probability of A. But if on the right-hand side, I restrict to the strip A, and now the probability of B is like 50%, because half the mass is in B. So that would not be. So these are independent independent events, but I don't get this as inequality. I think this example down here, it basically works because the probability of A and the probability of B based on area are going to be the same. Do you want to add to that? Yeah, go ahead. If they're disjoint, because then they're both equal to 0. Good. Good, yes. So if the numerator is 0, then it doesn't matter what probability of A and probability of B are. Right, okay, great. That's a great point. Or probability of A intersection B is equal to 0. Great. Yeah. Oh, the correct thing I would like to see in the exam is that this is not true. Right, yeah. So this is, in general, it's not true. There might be some cases where it's true, but in general, it's not true. Okay, and this is kind of an important thing to think about. One, you don't want to confuse them, right? You don't want to confuse probability of A given B with probability B given A. Those are not the same thing. So second, so the other thing, and I'll say a little bit more towards the end of the lecture, but in machine learning, you often are able to calculate one of these. You might be able to calculate probability of B given A, but you like to calculate probability of A given B. That's the relevant question to ask. And so you somehow want to convert from one to the other. And so Bayes' rule is, how do we convert from one to the other? So is there a question on? Yeah, so all right, so I'm seeing in the chat, A and B may have different sample size, so not equal. Right, so we haven't talked about samples yet. Sample size will come in the statistics section when we talk about you have actual data. And so but in general, when we're talking about probability, well, the sample space might be what is being asked. The sample space will be the same. We will talk about probabilities within the same sample space. Talking about probabilities within different sample spaces, they're hard to compare two different events. You have to kind of specify the sample space based on the restriction. Kind of having conditional probabilities is a way of changing the sample space. So in probability A given B, you're looking at the probability of A restricted to the sample space B, and in probability B given A, you're looking at the probability of B restricting the sample space to A, right? So, but the sample spaces in general, unless we condition things, are going to be the same. So hopefully that clarifies that question. Yeah. So okay, great. So this is not true in general. It might sometimes be true, but in general is not true. And the relationship between these is kind of a very important rule called, this is called Bayes' rule, okay? And this is named after Thomas Bayes, okay? So the apostrophe comes after the S. It's his rule, and his name ends in S, Phillips. So the apostrophe comes afterwards. Let me make sure that's a little bit more clear. Just otherwise, it's very common to misplace the apostrophe without thinking about this. So I'm going to write down the rule first. So we want to convert from probability of A given B, and we want to relate this to the probability of B given A. This is not true by itself, but we're going to add some other parts. Okay, so we're going to say this is equal if we multiply by the probability of A and divide by the probability of, of B here. Yeah. Okay. I've switched A and B with my notes. So okay. Yeah. So okay. So this is the rule. This rule is true, right? So if probability of A and B are equal, right? If these quantities are equal, then they cancel, and then we do get this equality that we asked on the previous slide, right? So in this rule is kind of the basis of kind of one branch of statistics called Bayesian statistics, and there are kind of there's not just two branches, but there's a controversy in in the right way to calculate statistics between the frequentist branch and the Bayesian branch, and so they have a very different viewpoints on how to approach doing statistics and data analysis. It's not a controversy about this rule. Sometimes rules are like meant to be broken. This is not a rule that's meant to be broken. This is a truth. This is an actual equality. Okay, and the controversy of Bayesian statistics versus frequentist statistics is more about where to put your assumptions in your modeling than in whether this rule is true or not. Okay, but this rule, and we'll mention this in kind of the second half of the lecture, kind of plays an important role in data analysis. So why is this true? Why is this equality true? And we started to work through this, but so I'm going to go and derive this rule, and I'm just going to expand this right-hand side. This is equal to the probability of A given B divided by the probability of B, right? And I also know that I've also got the rule that probability of B given A is equal to the probability of B intersection A divided by the probability of A, right? So this is also just the rule of conditional probability on the other side. But I can rewrite this a little bit to be probability of B given A times probability of A is equal to the probability of B intersection A, right? So I've just multiplied the probability of A on both sides. Okay, and now I'm going to go, and this is also equal to the probability of A given B. Okay, so now I'm going to apply this rule, this equality, into here, and I'm going to get probability of B given A times the probability of A divided by the probability of B, right? So I've just replaced this expression here, right here. So I've used this equality, and so I've moved kind of this term to here. Okay, and now, it's done. I've completed this. This term is same as this term. Okay, so it's just the definition of conditional probability. So it explains why this rule is true. Okay, so given the definition of conditional probability and a little bit of algebra and checking you're not dividing by zero someplace, then this rule is true, right? So this is, let me just highlight this rule. just so this still stands out in the notes, this is kind of an important rule. You should basically, you should basically memorize this rule, okay? So it's a little confusing which one is, in this right-hand side, which one is, do you multiply by probability of A or by probability of B? Well, the kind of idea is you multiply by the part you're so conditional on. So you have the probability of A given B times the probability of A, right? This is kind of like this chain rule that you had seen before. And so the probability B needs to normalize. You could also, if you moved this guy onto the left side, multiplied through by probability B, then it's so going to look like symmetric. But you should pretty much just memorize this rule. I think I've met someone who had this, like tattooed on them before. So I don't like totally advocate necessarily tattooing it, but it's because I don't think you need to tattoo it, because you should memorize this, by the end of class. You shouldn't need a tattoo to memorize it. All right, so okay. So let's go and try and use this in some examples. All right, so let's do an example. All right, so let's talk again with this two urns example, where I'm going to have two urns. Let's say urn 1 and urn 2, and the first urn's going to have it's going to have 4 of these black balls in the urn and 3 of the red balls, and urn number 2 is going to have 2 red balls and 2 of the black balls. And I'm going to choose one urn I'll choose the urns with equal probability, and then I'll choose a ball with like equal probability, right? And so we asked the question, so before, what's the probability that I choose a red ball, right? And we worked this out, that this was the probability I choose urn 1 times the probability I choose a red ball, which was 3 out of 7, plus, using the rule of total probability, the probability I choose the second urn times the probability I choose a red ball in that urn. And this was, let's see, do anyone remember what the answer was? So it's possible to need this in a second. So 3/14 plus, what's it, 3/6 plus, I think, 13/28. So does that look right? Yeah, so I think the answer is 13/28. Okay, the probability I choose a red ball. So what does that mean? What's the probability? I can write down the probability I choose a black ball is then going to be 15 out of 28, right? Because it's equal to 1 minus the probability of a ball that's red. Okay. Okay, so now, new question. So here's the question I want to ask. Given I conditioned on that I chose a black ball, what's the probability that I picked the first urn? Okay, so I want to ask the probability of choosing urn 1. Okay, choosing urn 1 conditioned on choosing a black ball. Okay, so if I know I chose urn 1, it's easy to calculate the probability I picked a black ball, right? I could also say, it's also easy to say that the probability of picking a black ball given urn 1, right? This is an easier thing to ask, right? Given I picked urn 1, the probability of picking a black ball is going to be 4 out of 7, right? So that direction is easy, but that's the wrong direction. I want a condition on picking a black ball, then what's the probability I picked earn one, right? So I need to swap which direction this so conditional is on. And to do that, I need to apply Bayes' theorem, right? So I expand this, the probability of a black ball given earn one times the probability of earn one divided by the probability of the black ball, right? So this is Bayes' rule, right? Okay, and I have all of these numbers are now pretty straightforward. So the first one, probability of black ball given earn one, this is 4 out of 7, okay? The probability of earn one, that was equally likely, so 1/2. And the probability of a black ball, well, I calculated that earlier, that was 15 out of 28. Okay. All right, now I have to do some multiplying fractions together here. Let's see, the numerator is going to be 8/14, so that's 16 out of 28, right? And so that makes this 16 out of no, 8 out of 28. So that makes it 8 out of 15. Yeah, so does that look right? Yeah, okay. So it's would have been hard if I didn't know Bayes' rule. It would have been kind of tricky to, to try and figure this out. The probability of earn one given the, given I drew a black ball. I probably could have used total probability to figure it out. I could have written out all the combinations and then conditioned on the black ball and divided. And I probably would have, I would get the same answer. But it's kind of more straightforward with Bayes' rule. Each of these things on the right-hand side was easier to calculate, or we had already, in this case, probably black ball, we'd already done this calculation. Okay, so Bayes' rule, made this a bit easier. Okay, any questions on how this works? All right, so let me give you another question, and I'll maybe ask you guys to work it out yourselves. Let's see. So this is a new example. Okay, so you're going to have great. So you're going to have kind of a, so this is for the electrical engineering people in the class. You're going to have a main, main power, and then you have a, backup power. Okay, and you're concerned that both the main power and the backup power go offline, and you have like a system which is kind of finicky. So it means that if there's like like a thunderstorm or it's extreme cold, maybe is a chance that the main power, the probability that it goes offline is, 0.1. So there's a 1% or a 10% probability that it goes offline with extreme cold. Okay. The probability that the backup goes offline with extreme cold is also going to be 0.1. Okay, so the probability that the backup goes offline is 0.1. So like under all events, but if you have to rely on the backup, then it needs to actually start running, and it's more likely to fail. Okay, so if the probability that the backup goes offline, given that the main power goes offline, this is now going to be higher. So is is going to be like 15%. So 50% of the time, the backup is going to fail if the main power also fails. Okay. Or given that the main power fails, then the backup is more likely to fail. Now it's going to fail like 15%. All right. So the question is, so I'm going to ask two questions. The first one, what is the probability that the hold on, I changed this slightly. So I'm going to say the probability that the backup fails given the complement that the main fails is so 0.1. So if the main is up and running, then the backup is only going to fail so 1% of the time. Okay, so I'm going to slightly change this. And then I want to ask you to figure out the probability that the backup is going to fail. Okay, so if the main fails, it's 1% of the time. If it's 50% of the time. If the main does not fail, it's so 10% of the time. Okay. So this is the first question. The second question is, so if the backup fails, okay, given that the backup fails, what's the probability that the main also fails? All right, for this one, you'll have to use BayesRule. So let's stop and kind of work. How about you talk amongst yourself, try and work this out, and we'll come back in just like a minute or two and discuss this. All right, so do you want to do some breakout rooms? Okay, and you can jump in the breakout rooms and discuss, or you can. What? Okay. Oh, yeah. Oh, yeah. People want to. So, probably closer rooms than that. Now that just knows, let them know 60 seconds will be reconvening. So okay, so let's reconvene and so okay, so who wants to help me with the answers? All right, so what is the probability B? Explain how how you'd calculate it. So okay, so what I think you want to do here. So what was so suggested was that the answer was the probability B given M plus the probability B given M, so complement. All right, so this is close to the right answer. Okay, so yeah. Yeah, so what we want to use here is the law of total probability, right? So the law of total probability is the probability of B, or is, let's say A is equal to the probability of A given C, or let's say, and so some sort of event times the probability of E plus the probability of A E, so complement times the probability of E, so complement, right? So when you look at the probability of B given M, that's saying you assume that M was true. So that's gonna right, if you remember, this is equal to the probability of B intersection M. They're both true divided by the probability of of M, and the probability of M is less than 1. So when you divide by, it's kind of increasing the probability. I've looked at the probability in restricted sample space here. So I need to apply the law of total probability instead, as was suggested here. This will be probability of M here, and this one also is probability of M complement. Okay, so I need to calculate the probability of B given M conditioned, or times the probability that M actually did occur. And then if M did not occur, then I can look at the probability of it happening given that it did not occur. Okay, so this is a little bit more complicated calculation then. So this would be probability B given M is 0.15 times the probability that M occurred, okay, 0.1, right? I have that. Now I need probability of B given M complement. That's 0.1. And now I need the probability M did not occur. So I need that probability too. I don't have that written up on the input. Oh, so go ahead. So in the middle there, yeah. So yeah, right. So probability of M complement is 1 minus the probability of M, so that makes it 0.9, right? Okay, and so this is my probability of B given M, and I'm sure someone has calculated this for me. Yeah, right there. 0.105. Okay, so slightly probability that the backup failed is slightly larger than 10%. Okay, so not so bad. Okay, good. So it's good we calculated that because I'm going to need this, right? So now we have this is equal to 0.105. That seems about right. So sometimes it's useful to kind of spot check. I have two values, 0.15 and 0.1. And so I'm taking a weighted average of these two things, right? There's 10% probability of one and 90% the other. The result should be somewhere in between those two, right? And 0.105 is in between those two values. And it should be closer to the one that is multiplied by a larger probability of occurring. Okay, so this pretty much checks out. It's closer to 0.1 and it's in between those two. Okay, good. So you gave me the number I didn't calculate, but I trust it because of this this check. This is useful to kind of think of it this way. Okay. Now we want to do probability of M given B, right? The probability that the main supply failed, given that the backup failed. So if I know the backup failed, what's probably the main supply fail? All right. So who wants to help me? So how do I solve this? Go ahead and agree. Good. So great, cool, great. So I want to apply Bayes' rule, so I can transform it into these three terms here. And it looks like we have all of these pre-calculated at this point. The hardest one was the probability that the backup failed, right? Which we did as the first question, right? So now I can plug in all of these values, probably of the backup failing, given that the main failed, is 0.15. The probability that the main failed, this was given 0.1, divided by the probability that the backup failed. And this was the tricky thing we calculated with law of total probability, 0.105. And the result is, so before we say the result, what do you think the result should kind of look like, right? What do we think what's kind of a guesstimate before we actually write down the value? Yeah. Oh, okay. Yeah. So these you're pointing to the 0.1 and the 0.105 are pretty close to each other. So they're almost canceling out. Yeah. So that's one good thing. But I'm thinking more of just looking at this quantity probability of the main failing given the backup by just looking at what we have in the input and what we've calculated so far, just intuitively, not like looking at like the numerics. Okay, so you're saying a little bit less than 0.15. I think a lot of what you said was actually good. You said it should be maybe similar. Like you said, the backup is slightly more likely to fail. But we know that but I would actually compare it to this quantity up here, the probability that the main is going to fail. This is about 0.1, right? So it's probably going to be, it doesn't seem like the backup failing has a lot of has a lot of influence on this. They're pretty close. The backup probability is about 0.1 or 0.15, whether or not the main is active or not. So they don't seem to have too much kind of influence on each other. So I expect it to kind of be so close to that, right? And then I expect, okay, the backup seems to be slightly less likely to, slightly more likely to fail. Okay, so probably the main fails given that the backup fails. Yeah, so so you said slightly less than 0.15. Yeah, so maybe slightly less than 0.15. Oh, and you're, yeah, I was going to say slightly more than 0.1, but okay, maybe your intuition is a little bit better, right? But these kind of ways of thinking about it, it should be in this ballpark. If I get a value greater than 1, you know it can't be, I made a mistake someplace. Should kind of be in this ballpark. All right, so let's see. Okay, who has calculated the actual answer? Oh, on Zoom? All right. 0.143. 0.143 about. Is that about what everyone else got completed? Okay, cool. Yeah, so okay, yeah, so it's kind of around 0.10% to 15%, you know, so somewhere in that range. Okay, good. So this is kind of how you apply Bayes rule, and this is the sort of things that kind of helps, you know, sort of helps you do these sort of calculations. All right, so this is kind of one straight up way within kind of within just probability of doing this. Let me talk a little bit for the last 15 minutes or so of Bayes rule in machine learning. Learning. Okay, so typically we think of two different. So I'm going to use kind of some. I'm going to use some events M and D, and this M is so going to represent that my model describes, you know, the world. Okay, so machine learning is often about observing data, assuming that data is randomly observed from the world, and then trying to produce a likely model of that world that fits the data. Okay, so I want to come up with a model of the world, and I want that to kind of, you know, that like fits the data. So the data is then kind of, you know, the event D is the data I collected. Okay, so when you're in machine learning, it's usually after you've collected the data. So it's a little bit weird. So that event has like always happened. Okay, but you want to write it so like that event conditioned on the model, right? So what we would like to do is we would like to find the probability of my model of the world given the data that I've collected. Okay. And in fact, we wouldn't just like to calculate this, but we're actually going to consider a bunch of different models of the world and find the one that has the highest probability. Okay. If we can write down this function and calculate it for any possible model, then we can try a bunch of models and say which one is the best one. Right. And that's the one we're going to say, that model is a good representation of the world because that's the most likely given my data. It turns out this by itself is hard to, is like hard to calculate. What is the probability of my model given, the data? That's what we would like to do, but it's easier often to calculate it through, Bayes' rule. Right, so we transform it to the probability of the data given the model times the probability of, the model divided by the probability of, the data. All right, okay, so some of these things, and these things are, or some of these quantities on the right-hand side are now easier to calculate. Okay, and not all of them, some of these don't actually make a lot of sense. What is the probability of, the data? Okay, well, I've collected the data, so I know that that's true. So this term kind of, well, it turns out that it's actually the probability that I collected the data given what the real world actually is. And so if you make an observation, we'll talk about might not actually be a probability. It might be of the probability 0 of actually happening. But this term, does not matter at all. What I'd like to do is find the model which maximizes this probability. This term, this expression on the left here, the probability of the data, that's going to be the same value independent of which model I choose. So if I want to maximize the data, I don't need to worry about this denominator. Sometimes this is something that in simple discrete cases, you can sometimes calculate the denominator, but you usually don't need to. Okay, so we're going to kind of cross this out and say this is about the probability of the data, given the model, times the probability of, the model. It's about the right thing. It's called proportional to. They're the same up to some constant. I don't need to know what that constant is. Okay? So then I just want to maximize the model. I want to be able to calculate these two terms. Okay. The probability of the model. Okay, so this term is also sometimes interesting. This is often called the prior. Okay, so if I have a prior knowledge about which models are more likely of the world, then I might say this model is more likely than the other model. Sometimes I use this in machine learning to say one model is simpler than the other model, right? So I would rather have a simpler model than a more complicated model. More complicated model might look like it does well in the data, but then it doesn't generalize to new data that I haven't seen yet. So often in this prior, you kind of give more probability to models which are simpler or ones that I might have some prior knowledge about stuff. And I'm going to say that's more likely. Yeah. Yeah, so overfitting is something in machine learning where you pick a model of the world that's very complicated and it fits all the events you have, right? So let's say I have a stock market and I'm trying to predict what the next price of the stock is. This, basically does not work. Okay, it works maybe on some very short intervals, and that's where high-speed trading works. But otherwise, over any kind of general period of time, this doesn't work so well. But let's say I had all this historical data of the price of the stock, and I fit a model that was very complicated. It hit every price point exactly. Well, so what this might look like is I have time, right? And I have the price of the stock, and I have a whole bunch of kind of weird kind of values. And I might try and fit a model that goes through here, and it hits every data point exactly. I missed one. Okay. And then I want to predict what happens next. Well, this model might, right, it hit each of these data points, but the model might say, oh, it does this next, right? Or it might go down like this. I don't know. A very complicated model, might do that, whereas a simpler model might say, well, it kind of is going like this. It's kind of a line. There's some error off that line, but for the most part, it looks kind of like a line, right? And so this would be a simpler model. I might trust the green one more than the really complicated one that's red. And so you might want to say, well, somehow encode in that probably the model that the green one is more likely than the red one. And that's what a prior sort of would do here. And this would help regularize to try and prevent overfitting, where you try and fit the data perfectly, but when it may not work well on data that's new. Yeah. Yeah, but that's a different issue, right? So so most of machine learning, and we'll talk about this a little bit more in like statistics. It has the view that your data is actually going to be a set of observations up to say xn, and these are independent observations. These are independent. And so what that means is that the probability of D is going to be equal to the probability of x1 times the probability of x2 times the probability of x3, and so on. Because I assume they're independent, and I assume they're representative of the world, I can calculate them by taking, the product of them, the product of these probabilities. And I assume that they're all representative of the same world. They're all observations, they're independent observations of the same world. If the world changes after I drew all my samples, well, then those are no longer sort of representative of that. Okay, so at that point, so what do you do, right? You can maybe try and get a little bit of new data and estimate how it's changed, and that's one thing you can try and do, and that's kind of a common approach. But if stuff completely changes under your feet, then there's not much you can use the old data for if it has no relation to the new data. If it's correlated, if the new data is, if the old data is not independent of the new world, right, you can get some information from it. Okay, but if the old data observations are independent of the new world, then that's not going to help. All right, so this part of the model, this probability right here, this is called the prior, and this can be helped to kind of guide you towards a more likely kind of model that's used, but this has to come in without looking at the data. This has nothing to do with the data. Okay, so this is kind of your prior knowledge about the world or your prior assumptions, or tells you about, I'd like something simpler instead. Okay, and what's left is the probability of the data given the model. Okay, so what is the probability of the data so given the model? Well, as I mentioned, I can often write the probability of the data. Let me write this more clearly. The probability of the data, I can often write it as the product of the probability of the first data point, the probability of this second data point, and so, just the product of these observations. And so if I have x1 here, right, and I have a line, I kind of get this error on this line, right? At this time point, ti, I might, if this is xi, I might my model, M of TI might say, well, I think the value is going to be right there, but I might have some error. So it's going to be there with some error. And I can decide an error model. Again, this is a modeling choice. And I can say, well, it's going to be here with some probability, some distribution that it varies off of here. And we'll need to describe this with kind of continuous random variables later in the,
I will say you should be thanking me
So
for
the
tearing up your
semester?
beach because
But
I
if,
got you like 4 pi over
uh,
sand.
All right. So if you can, if I have this model, I can often calculate the probability of some data point given this model, right? So the model, the green line, I can say, well, the distance from the green line is something, and so that happened with some probability. Actually, it's probably not a probability, it'll be what's called a likelihood. But I can often calculate that given a model. Now, if I don't know what the model is, I don't know how to calculate that. It's hard to do the inverse. But if I have a guess of the model, I can calculate this. And so this makes, trying to optimize the most likely, the highest probability model, it's easier to calculate this term, the one data point, how likely was I to see that given a guess of what the model was? And Bayes' rule allows me to twist that around, okay? And so this is really kind of, if you take the foundations of, the foundations of data analysis class, this is kind of the first several lectures kind of builds up to using Bayes' rule in this way, and you'll kind of, see how to calculate all these things on, examples. But this is one reason why kind of Bayes' rule is kind of one of the cornerstones of machine learning. So you should, this is kind of one of the prerequisites to get into machine learning. You need to know what Bayes' rule is and kind of how to use it. And then there's a bunch of ways you can come up with not just a model of a line and stuff like that, but also kind of how to build classification and things like, like GPT chat eventually down the line. So, okay, so any questions on this stuff? Okay, we'll stop here and then we'll talk about discrete random variables on Thursday. And if you want to get a copy of the homework, I've got some printed out up front here.